Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in wherever you are. Let your body sink into comfort, releasing whatever tensions the day has left behind. There's nowhere you need to be, nothing you need to accomplish. Just gentle exploration ahead. Where in the world are you right now? A quiet room where you can finally let your mind rest. A peaceful space where the day's noise has faded. Wherever you are, you're exactly where you need to be. Tonight we're going to explore something unusual in science, a phenomenon where increased study brought not clarity but deeper mystery, where each answer revealed more questions, where the more data we gathered, the less certain we became. We'll discover how 3I/Atlas, the interstellar comet that visited our solar system in 2024, became progressively stranger the more carefully we observed it, defying expectations and challenging our understanding of what comets should be. But don't worry. This isn't going to be a frustrating journey through confusion or unsettling encounters with the unknown. Instead, we'll move slowly and thoughtfully through the observations that accumulated, the anomalies that emerged, and the deepening appreciation for how complex and surprising natural phenomena can be. By the end, I think you'll find not anxiety about uncertainty, but peace in embracing the limits of knowledge and beauty in questions that resist easy answers. If you enjoy these calm explorations of cosmic mysteries and scientific puzzles, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in now. Let your shoulders drop. Releasing tension you didn't know you were carrying. Take a slow, deep breath in, feeling your lungs expand and release it gently. Feel yourself sinking deeper into comfort with each exhale, and let's begin our slow drift through the paradox of 3I/Atlas, exploring how scientific investigation sometimes reveals not answers, but richer, more fascinating questions. There's nowhere you need to be, no conclusions you must reach. Just listen, and let the mystery unfold like the patient work of astronomers gathering data that refuses to resolve into simple patterns. Let's begin with how straightforward 3I/Atlas seemed at first, because appreciating the deepening mystery requires understanding how normal everything appeared initially. The discovery came in January of 2024 from the Asteroid Terrestrial Impact Last Alert System, ATLAS, an automated survey designed to find potentially hazardous asteroids and other moving objects in the night sky. When the object was first detected, it appeared as a faint point of light moving against the background stars. This is how all asteroids and comets are discovered, by their motion making them stand out from the stationary stars. The initial observations were routine. The object was faint, roughly magnitude 20, visible only to large telescopes. Its motion suggested it was somewhere in the outer solar system, though the exact distance couldn't be determined from just a few observations. Within days, as more observations accumulated from multiple telescopes, astronomers calculated a preliminary orbit. This is standard procedure for newly discovered objects, using the positions measured at different times to work out the trajectory. The orbital calculation revealed something immediately interesting. The orbit was hyperbolic. The eccentricity, a measure of how elongated an orbit is, came out greater than 1. Hyperbolic orbits are unbound, meaning the object has enough energy to escape the sun's gravity permanently. Finding 3 interstellar visitors in 7 years suggested they were common, arriving perhaps once or twice per year. Better surveys were simply finding more of them. The initial spectroscopic observations were equally unsurprising. When astronomers pointed spectrographs at 3I/Atlas to analyse the light it reflected, they saw signatures consistent with a comet. Water vapour emission lines appeared in the spectrum. Carbon monoxide and carbon dioxide were detected. These are typical cometary volatiles, ices that sublimate when heated by the sun. The object had developed a coma, the fuzzy cloud of gas and dust that surrounds an active comet nucleus. The The coma was visible in images as the object's apparent size exceeded what a point-like nucleus would show. A faint tail was detected extending behind the comet, pushed by solar radiation pressure and the solar wind. This is normal behaviour for comets inside about 3 astronomical units from the Sun. Everything about 3I/Atlas's appearance and behaviour matched expectations for an interstellar comet. It was like 2I/Borisov, which had behaved essentially like a normal solar system comet despite its interstellar origin. The size was estimated from the brightness, an assumed albedo, the fraction of light reflected. The nucleus appeared to be roughly 3 kilometres across, perhaps a bit smaller or larger depending on exactly how reflective its surface was. This was a reasonable size for a comet. Most comets are a few kilometres across, though the size distribution extends from tiny fragments to giants like Hale-Bopp, that was roughly 40 kilometres. The composition appeared typical. The ratio of different volatiles, the dust-to-gas ratio, the colours and reflectance properties, all fell within the range seen in solar system comets. If anything, 3I/Atlas seemed almost disappointingly normal for an object that had travelled between stars. It was just another comet, happening to be on a hyperbolic trajectory but otherwise unremarkable. The scientific papers published in the first months after discovery described it in matter-of-fact terms. An interstellar comet, likely ejected from another planetary system billions of years ago, now passing through our solar system on its way back to interstellar space. The trajectory brought it to perihelion, closest approach to the Sun, in late May of 2024. The perihelion distance was calculated at 0.39 astronomical units, inside Mercury's orbit but not dangerously close. This was well within the range of typical cometary perihelia. Many comets pass perihelion at similar or even much closer distances. There was nothing unusual about the orbit itself beyond being hyperbolic. Predictions were made for how bright the comet would become, when it would be best observable, what observing strategies would maximise scientific return. The observation campaign was planned with confidence based on how comets typically behave. Everything was proceeding according to understanding. The comet was being observed, data was accumulating, and the picture that emerged was coherent and sensible. This initial simplicity is important to remember. 3I/ATLAS started as a straightforward object that fit neatly into existing knowledge. There was no mystery, no confusion, no sense that anything was unusual. But as observations continued and more sophisticated instruments examined the comet in greater detail, cracks began appearing in this simple picture. Small anomalies emerged, each one perhaps explainable on its own but together suggesting something wasn't quite right. The transition from simple to mysterious didn't happen suddenly. It was gradual, like watching a photograph develop in reverse, starting sharp and clear but becoming progressively more blurred and ambiguous the longer you looked. By the time 3I/Atlas faded from view in late 2024, astronomers were left not with clear understanding, but with a collection of puzzling observations that resisted coherent explanation. The journey from that initial simplicity to the eventual perplexity is the story of how science sometimes reveals not answers but questions, how nature refuses to conform to our expectations, and how the universe retains its capacity to surprise us. The first hint that 3I/ATLAS might be more complicated than initially thought came from careful measurements of its brightness over time. Comets vary in brightness for several reasons. They get brighter as they approach the Sun, and heating increases sublimation. They get dimmer as they recede and activity decreases. They can also vary due to rotation bringing different regions into view, or from outbursts of sudden activity. Astronomers have extensive experience with cometary brightness behaviour. There are empirical formulas relating brightness to solar distance that work reasonably well for most comets. When these formulas were applied to 3I/Atlas's brightness measurements, they didn't quite fit. The comet was behaving differently than the formulas predicted. Initially, this wasn't concerning. Every comet is unique. The formulas are averages that capture typical behaviour, but don't perfectly describe any individual comet. But as more data accumulated, the deviation from expected behaviour became more pronounced. The comet was getting brighter faster than it should as it approached the Sun, and the brightness increases didn't follow the smooth pattern that solar heating alone would produce. There were irregularities, bumps and dips in the brightness curve that suggested something more complex than simple sublimation from solar heating. One possible explanation was that the nucleus was rotating, and different sides had different compositions or different amounts of ice. As rotation brought more active regions into sunlight, brightness would increase. As less active regions rotated into view, brightness would decrease. This explanation required specific assumptions about how the ice was distributed on the nucleus. The surface would need to be quite heterogeneous, with some areas much more volatile rich than others. While not impossible, this was somewhat unusual. Most comets show relatively uniform activity around their surfaces, or at least variations that follow simpler patterns. Attempts to fit the brightness variations with rotation models ran into problems. The rotational period couldn't be determined consistently. Different datasets gave different rotation rates, or the brightness variations didn't repeat with the regularity that rotation would require. High-resolution imaging was attempted to look for multiple condensations that would indicate fragmentation. Some images seemed to show elongation, or possibly multiple peaks in the brightness distribution. But the comet was far enough away that definitive confirmation was difficult. The fragmenting hypothesis also had problems explaining the detailed brightness behaviour. The timescales didn't quite match what models of fragmentation predicted. None of the standard explanations, rotation, outbursts, or fragmentation, seemed to fully account for what was being observed. Each could explain some aspects of the data, but left other aspects unexplained. This was the first sign that 3I/ATLAS might not be a standard comet. The brightness behaviour was anomalous in ways that existing models couldn't quite capture. At this stage, the anomaly was subtle. It wasn't that the comet was doing something impossible, just that it wasn't fitting neatly into expected categories. The data was noisy, the observations challenging, and reasonable people could disagree about whether there was truly anything unusual or just normal cometary complexity. But the unease had started. Researchers studying the brightness data were finding it difficult to construct simple, convincing models that matched all the observations. Something seemed off, even if exactly what was unclear. The brightness anomaly became a topic of discussion at conferences and in email exchanges among the observers. Was anyone else seeing this? Did anyone have a good explanation? The consensus was that 3I/Atlas was, quote, zero in ways that normal comets weren't. This early anomaly set the pattern for what would follow. Each new observation, each additional data set seemed to reveal new complexities rather than resolving existing ones. The comet was fighting back against attempts to understand it, remaining stubbornly mysterious. The brightness variations continued throughout the observation period, never quite settling into patterns that matched any single explanation. By the time the comet faded from view, the brightness behaviour remained one of several puzzling aspects that defied simple interpretation. This first anomaly was like a loose thread in fabric. Pull on it gently and it seems minor. But keep pulling and you realise it connects to deeper structural issues, unravelling the simple picture you started with and revealing something more complex underneath. As 3I/Atlas came closer to Earth and to the Sun during its approach to perihelion, higher resolution observations became possible, revealing another puzzle. The shape of the nucleus was behaving strangely. Determining the shape of a small distant comet nucleus is challenging. The nucleus itself is typically only a few kilometres across, far too small to resolve as an extended object from Earth, even with large telescopes. But there are indirect methods. The light curve, how brightness varies with rotation, contains information about shape. An elongated object shows larger brightness variations as it rotates than a spherical object does. The spectrum of polarization, how the reflected light is polarized also depends on shape and surface properties. And if you can get very high resolution imaging, sometimes the nucleus appears slightly elongated rather than perfectly point-like. When these methods were applied to 3I/Atlas in February and March of 2024, they suggested the nucleus was elongated, with a length-to-width ratio of roughly 2.8 to 1. This was unusual but not unprecedented. Some comets are elongated, possibly from being contact binaries where two objects are touching, or from tidal forces during close approaches to planets, or simply from irregular accretion during formation. 1I/Oumuamua, the first interstellar object, had been extremely elongated, possibly 6 to 10 to 1 ratio, though its exact shape remained uncertain and controversial. So an elongated 3I/ATLAS was interesting but explainable. It fit the emerging picture of interstellar objects potentially being more diverse in shape than typical solar system comets. But here's where it got strange. The elongation ratio appeared to be changing over time. Several explanations were proposed. One was that the nucleus was fragmenting, breaking into pieces that were separating slowly. From a distance, separating fragments might look like an elongating single object if the separation was gradual and the pieces remained relatively close. This could explain the shape change. But it required quite specific fragmentation behaviour. The pieces would need to be separating at very low velocities, perhaps meters per second, and they would need to be staying aligned along one axis rather than drifting randomly. 3I/Atlas was marginally detectable in radar in March of 2024 when it passed relatively close to Earth. The radar data was noisy but seemed to show a bimodal structure, possibly two lobes or an elongated single object. But when the radar data was analysed to estimate elongation, it gave values inconsistent with the optical observations from the same time period. Either the radar was seeing something different than the optical telescopes, or one or both measurements were being misinterpreted. The confusion multiplied when different research groups analysed the same data and reached different conclusions. Some papers reported clear evidence of progressive elongation. Others argued the data was consistent with constant shape if you accounted for uncertainties properly. Scientific conferences featured debates about 3I/ATLAS's shape. Presentations showed different models, different interpretations, different levels of confidence in the reality of the shape change. No consensus emerged. The more carefully people looked at the shape question, the less clear it became. The data was right at the edge of what current instruments could measure, in a regime where noise and systematics made interpretation ambiguous. By June, after perihelion when the comet was receding, attempts to measure shape became even more difficult as the comet faded. The question of whether the shape had actually changed remained unresolved. What could be said with confidence was that something about 3I/Atlas's geometry was unusual. Whether that unusual aspect was changing shape, fragmenting structure, peculiar surface activity patterns, or some combination remained unclear. The shape problem illustrated a recurring theme in the 3I/ATLAS story. Observations that seemed precise enough to measure something interesting, but turned out to be just ambiguous enough to resist definitive interpretation. It was like trying to read text that's slightly too far away to focus on clearly. You can see that there's writing there, you can make out some of the letters, but you can't quite read the full message no matter how hard you squint. The shape anomaly joined the brightness anomaly in the growing list of aspects of 3I/ATLAS that seemed to be telling us something important, but remained frustratingly unclear about exactly what that something was. As 3I/Atlas approached perihelion and its activity increased, spectroscopic observations intensified, revealing perhaps the deepest mystery of all. The composition didn't make sense in consistent ways. Spectroscopy works by dispersing light into its component wavelengths, revealing which atoms and molecules are present by their characteristic emission or absorption lines. It's one of astronomy's most powerful tools for determining what distant objects are made of. Comets have well-studied spectroscopic signatures. Water vapour produces strong emission lines throughout the spectrum. Carbon monoxide, carbon dioxide, cyanogen, hydroxyl radicals, and many other molecules contribute characteristic features. By measuring the strengths of different spectral lines and comparing them to models, astronomers can determine the relative abundances of different volatiles and learn about the comet's composition. For 3I/Atlas, spectroscopic observations began in February when the comet was still faint but showing detectable emission. The early spectra looked normal, showing the expected molecular features at reasonable intensities. Water was clearly present and appeared to be the dominant volatile, as expected for a comet. Carbon monoxide and carbon dioxide were detected at levels typical for comets. Everything seemed standard. But as more spectroscopic observations accumulated from different telescopes and different wavelength ranges, inconsistencies began appearing. The ratio of carbon dioxide to water appeared to change with time. Early observations suggested relatively high carbon dioxide abundance, perhaps 20% of water. Later observations showed lower carbon dioxide, perhaps only 5% of water. Volatile ratios in comets can change as different ices sublimate at different rates, so this variation wasn't necessarily problematic. But the magnitude of change was larger than expected, and the pattern didn't follow what models of selective sublimation predicted. More troubling were unidentified spectral features. Several emission lines appeared that didn't match any known cometary molecule. These features were weak, near the noise level, but they appeared consistently in multiple observations from different telescopes. Attempts to identify the mystery lines led nowhere. They didn't match water or any common carbon or nitrogen compound. They didn't match any molecules known to exist in comets or in the interstellar medium. The 3.4 micron feature, attributed to carbon-hydrogen bonds in organic molecules, was weaker than expected given the strength of other organic features. This suggested an unusual mix of organic compounds, different from what's seen in most comets. The deuterium to hydrogen ratio itself, when it could be measured from certain spectral lines, gave inconsistent values. Some measurements suggested enhancement over solar system values, others suggested depletion. The uncertainties were large, but even accounting for uncertainties, the values didn't seem to be converging on a consistent answer. Isotopic ratios are important because they provide clues about formation conditions. Different parts of a protoplanetary disk, or disks around different stars, produce materials with different isotopic signatures. If 3I/ATLAS had a clearly unusual isotope ratio, it would indicate formation in an environment different from where solar system comets formed. But the measurements were too inconsistent to draw clear conclusions. The nitrogen to carbon ratio was also peculiar. Nitrogen is detected through emission from CN, the cyanogen radical. Carbon comes from multiple sources, but primarily carbon monoxide and carbon dioxide. But even accounting for these challenges, 3I/Atlas seemed more inconsistent than normal. The spectroscopic data resisted coherent interpretation more stubbornly than it should have. By the time the comet faded from view, no consensus existed on its detailed composition. Everyone agreed water was the dominant volatile and that the comet contained dust and organics. But beyond that basic picture, specifics remained contentious. The spectroscopic confusion illustrated another aspect of the deepening mystery. Not only did we not fully understand 3I/Atlas, we couldn't even agree on what the observations were telling us. In science, disagreement about interpretation is normal when data is ambiguous. But usually, as more data accumulates, disagreement decreases. More measurements narrow the possibilities and guide convergence toward truth. With 3I/ATLAS, the opposite seemed to happen. More spectroscopic data led to more disagreement, more alternative interpretations, more questions about what was actually being measured. It was as if the comet was deliberately obscuring its nature. presenting observations that could be read multiple ways depending on your assumptions and analysis choices. The spectroscopic confusion, like the brightness and shape anomalies before it, suggested that 3I/ATLAS was something more complex than a typical comet. But complex in what way remained frustratingly unclear. The orbit of 3I/Atlas, initially seeming straightforward, revealed its own puzzles when examined in detail, adding another layer to the accumulating mystery. Orbital determination for comets is complicated by non-gravitational forces. As ice sublimates asymmetrically, gas jetting from the nucleus acts like tiny rocket engines, pushing the comet and slightly altering its trajectory. These non-gravitational accelerations are typically small, perhaps modifying the orbit by hundreds or thousands of kilometers over months, but they're measurable and need to be accounted for when predicting where the comet will be. For most comets, non-gravitational accelerations follow understandable patterns. They're strongest near perihelion when sublimation is most intense. They tend to push the comet in predictable directions related to where the Sun is and how the nucleus is rotating. Models exist that describe typical non-gravitational behavior based on decades of cometary observations. These models work reasonably well for most comets, allowing orbital predictions accurate to within small margins. When these standard models were applied to 3I/ATLAS, they didn't work very well. The comet's position deviated from predictions in ways that the standard, non-gravitational models couldn't account for. More sophisticated models were tried, allowing for more parameters and more complex activity patterns. These fit the observations better, but required assuming unusual outgassing geometry or activity variations that seemed contrived. The pattern of non-gravitational acceleration didn't follow the expected correlation with solar distance. It varied on timescales that didn't match the expected response to changing solar heating. One possibility was that the rotation state was complex, perhaps tumbling rather than rotating smoothly around a single axis. Tumbling would create time-variable outgassing directions that might explain the trajectory deviations. But there was no independent evidence for tumbling from light curves or other observations. The rotation period, to the extent it could be determined at all, seemed fairly stable. Another explanation was that the nucleus had active areas that turned on and off unpredictably, perhaps from exposure of fresh ice or from structural changes. This could create erratic outgassing that would affect the trajectory irregularly. This explanation was plausible but essentially unfalsifiable. You could always invoke changing activity to explain any observation, without understanding why activity would change in particular ways. It wasn't really explaining anything. A more troubling possibility was that the non-gravitational accelerations weren't purely from outgassing. Perhaps there were other forces at work, forces not accounted for in standard cometary dynamics. One speculative idea was that 3I/Atlas might have unusual charge properties. Comets can become electrically charged from solar-wind interactions and from emission of electrons when dust is hit by ultraviolet radiation. If the charge was substantial, electromagnetic forces from the interplanetary magnetic field might affect the trajectory in addition to gravity and outgassing. This was a highly speculative idea with little observational support, but it was hard to rule out completely. The trajectory puzzle deepened when attempts were made to trace the orbit backward to determine where 3I/Atlas came from in the galaxy. The hyperbolic orbit's direction and excess velocity allowed calculating where the comet was located millions of years ago, when it was far from the Sun and gravitational perturbations were negligible. Tracing back the trajectory suggested 3I/Atlas had arrived from the direction of the constellation Canes Venatici. The exact stellar neighbourhood it came from depended on how long it had been travelling through interstellar space and how much its path had been affected by gravitational interactions with other stars. Different researchers tracing back the orbit with slightly different assumptions about the non-gravitational forces reached different conclusions about the origin direction. The uncertainty in the backtracing was larger than desired. This made it difficult to identify a specific stellar system that might have been the comet's birthplace. Several candidate stars lay in roughly the right direction at roughly the right distance, but none was a clear match. Most likely, 3I/Atlas would wander the galaxy for millions of years before approaching another star close enough to be perturbed significantly. But the exact timeline was uncertain within factors of several. The trajectory puzzle, like the other anomalies, illustrated how 3I/Atlas resisted precise characterization. Every measurement was just ambiguous enough. Every model required just enough free parameters that clear conclusions remained elusive. It was becoming a pattern. Each aspect of the comet that astronomers examined, brightness, shape, composition, trajectory, revealed complexities that exceeded what simple models could explain. Whether these complexities reflected genuinely unusual properties or merely the challenges of observing a faint, distant object with limited data remained an open question that different researchers answered differently. But the accumulation of puzzles was undeniable. 3I/ATLAS was not a straightforward object. The more it was studied, the more questions emerged, and the less confidence anyone had in their understanding of what they were looking at. As the anomalies accumulated, scientists proposed various explanations to account for 3I/Atlas's unusual behaviour while keeping it within the framework of natural cometary phenomena. The most conservative interpretation was that 3I/Atlas was simply a typical comet, with properties that happened to lie at the extremes of natural variation, combined with observational challenges that made it appear more mysterious than it really was. Comets are diverse objects. No two are exactly alike. They vary in size, composition, structure, rotation state, activity patterns, and nearly every other property you can measure. Perhaps 3I/Atlas just happened to combine several unusual but not impossible properties: elongated shape on the edge of the distribution, composition slightly different from solar system average due to forming in a different stellar environment, complex activity driven by heterogeneous surface properties. The brightness variations could be explained by a nucleus with very unevenly distributed ice. If most of the surface was relatively inactive but concentrated patches were highly active, rotation would bring these patches in and out of sunlight, creating complex brightness changes. This natural comet hypothesis had the virtue of requiring no new physics and no extraordinary assumptions. It explained everything through known processes, just with parameters chosen from the tails of distributions rather than the means. The challenge for this hypothesis was that it required several unlikely things to be true simultaneously. Each individual anomaly could be explained as natural variation, but having all of them present in one object seemed improbable. Statisticians talk about the multiple testing problem. If you look at enough properties, you'll eventually find some that are unusual just by chance. But 3I/Atlas seemed to be unusual in too many ways for pure chance to be a satisfying explanation. Advocates of the natural comet hypothesis argued that this reasoning was suspect. We only study objects that catch our attention by being somehow unusual. There's an observational selection effect where the objects we observe most carefully are precisely those with anomalous properties. Perhaps there are many comets as peculiar as 3I/Atlas, but we don't notice them because we don't study them as intensively. The very fact that it was an interstellar visitor meant it received far more attention than a typical comet would. This selection effect argument had merit but was hard to test. We couldn't easily go back and analyse solar system comets with the same intensity to see if they showed similar levels of unexplained complexity. The natural comet hypothesis also had to explain why the two previous interstellar objects, 1I/Oumuamua and 2I/Borisov, were so different from each other and from 3I/Atlas. 2I/Borisov had been remarkably normal, showing behaviour indistinguishable from solar system comets. 1I/Oumuamua had been highly anomalous, possibly not even a comet at all based on its lack of observed activity. If interstellar objects were simply comets from other stellar systems, why would they show such extreme diversity? Was the sample of 3 too small to draw conclusions? Or was the diversity telling us something about the variety of formation environments around other stars? The natural comet hypothesis suggested that the diversity was real and reflected the wide range of conditions in different protoplanetary disks. Some produced normal comets like 2I/Borisov. Others produced unusual objects like 1I/Oumuamua and 3I/Atlas. This explanation required stellar systems to be more diverse than our own planetary system history suggested. But with only one example, our solar system, we had no strong basis for assuming other systems would be similar. The natural comet hypothesis thus served more as a placeholder than a satisfying explanation. It said, in essence, quote 2, without specifying exactly what variation was occurring or why. It was an appeal to normality, a bet that nature was being conventional rather than exotic. A reasonable bet, perhaps. But one that left the specific puzzles of 3I/Atlas unresolved and unexplained. Another interpretation that gained traction was that many of 3I/Atlas's anomalies could be explained if the nucleus was fragmenting, breaking into pieces during its passage through the inner solar system. Cometary fragmentation is common, though the causes and mechanisms remain imperfectly understood. Thermal stress from solar heating is one trigger. Tidal forces during close approaches to planets or the sun can cause breakup. Rotational stress from spin-up as ice sublimates can split weakly bound nuclei. High-resolution imaging attempted to directly detect fragmentation by looking for multiple condensations in the coma. Some images did show elongation or possible secondary peaks in brightness distribution, but the interpretation was ambiguous. Was the elongation from separated fragments or from an elongated single nucleus? Were the brightness peaks from discrete pieces or from activity patterns on a rotating nucleus? But later observations didn't show obvious multiple nuclei. Either the fragments were too faint individually to detect, or they hadn't actually separated, or the fragmentation interpretation was wrong. Theoretical modelling of fragmentation suggested it could reproduce some but not all of the observations. The brightness evolution could be matched if you assumed specific properties for the fragments and specific separation velocities. But the models had many free parameters: number of fragments, sizes, separation speeds, activity levels, compositions. By adjusting these parameters, you could fit almost any observations. This flexibility was both a strength and a weakness. The fragmentation scenario could explain a lot, but it could explain almost anything, making it hard to test rigorously. An alternative version of fragmentation proposed that the nucleus was gradually crumbling rather than splitting into discrete pieces. Instead of a few large fragments, perhaps it was shedding many small pieces continuously. This gradual disintegration could explain why no clear secondary nuclei were observed. The pieces would be too small to see individually, but collectively would affect brightness and other properties. The crumbling hypothesis still faced challenges. The timescales didn't quite match expectations. The coma's appearance didn't show some of the features that crumbling nuclei typically display. The role of fragmentation in explaining 3I/Atlas's behaviour remained uncertain. Almost certainly some fragmentation occurred, as it does for most active comets. The question was whether fragmentation was the primary driver of the anomalies, or just a contributing factor among several. Different research groups had different opinions. Some papers emphasised fragmentation as the likely explanation. Others argued it was insufficient to account for all the observations. The fragmentation scenario illustrated how proposed explanations could be simultaneously promising and incomplete. Yes, breakup could explain some things, but it left other things unexplained, and the evidence for it was suggestive rather than definitive. This pattern of partial explanations was recurring throughout the 3I/ATLAS investigation. Each hypothesis could account for some subset of observations but struggled with others. No single explanation tied everything together neatly. Whether this reflected the limitations of available data, the genuinely complex multi-causal nature of what was happening, or the possibility that the right explanation hadn't yet been proposed, remained an open question. The fragmentation scenario contributed to the sense that understanding was deepening but clarity was not. We had more ideas about what might be happening, but we weren't necessarily closer to knowing what actually was happening. Some researchers focused specifically on the spectroscopic puzzles, proposing that 3I/Atlas had genuinely unusual composition that reflected exotic formation conditions in its origin stellar system. This interpretation took seriously the unidentified spectral lines, the unusual volatile ratios, the peculiar organic signatures. Rather than dismissing these as measurement artifacts or normal variation, it treated them as real signals indicating something special about the comet's chemistry. The hypothesis was that the protoplanetary disk where 3I/Atlas formed had a chemical composition significantly different from the solar nebula where our comets formed. The unidentified spectral lines might be from molecules that don't form easily in solar composition material, but would be favoured in a chemically distinct environment. This explanation was intellectually satisfying in some ways. It connected 3I/ATLAS to broader questions about chemical diversity in the galaxy and about how planetary system formation varies with stellar properties. But it faced significant challenges. To explain the magnitude of compositional differences suggested by some observations required quite extreme chemical anomalies in the parent disk. Theoretical models of protoplanetary disk chemistry were consulted to see if they could produce such anomalies. The answer was maybe, under special circumstances, but it required fine-tuning conditions. The parent star would need unusual abundance patterns. The disk would need specific temperature structure. Mixing and transport processes would need to operate in particular ways to preserve the chemical signatures. Each requirement was individually plausible, but together they seemed contrived, specially tailored to explain 3I/ATLAS, rather than emerging naturally from stellar and disk physics. Another challenge was that 2I/Borisov, also an interstellar comet, had shown composition entirely consistent with solar system comets. If formation in different stellar systems could produce exotic chemistry, why was 2I/Borisov so normal? Perhaps different stellar environments produced different results. 2I/Borisov might have come from a system very similar to ours. 3I/Atlas might have come from a more unusual one. This answer worked, but required believing we'd happened to detect one normal and one highly unusual interstellar comet in our first three examples. Possible, but the probability was hard to assess. The compositional anomaly interpretation also struggled with the inconsistency of the spectroscopic measurements. If the composition was genuinely unusual, shouldn't all measurements show the same unusual signature consistently? Future observations of other interstellar comets could test whether exotic compositions were common or rare. If most showed normal chemistry like 2I/Borisov, that would argue against the compositional explanation for 3I/Atlas. But if subsequent interstellar visitors showed diverse chemistries, that would support the idea that different stellar systems produced comets with different compositions, and 3I/ATLAS was genuinely unusual in its chemical makeup. Until that future data arrived, the compositional anomaly interpretation remained speculative. An interesting hypothesis that could explain some observations but couldn't be verified or falsified with available evidence. It illustrated how the ambiguity of the 3I/Atlas data created space for multiple competing hypotheses that were all consistent with observations, but that made different predictions and had different implications for our understanding of planetary systems. A more skeptical interpretation suggested that there was no real mystery at all. That 3I/Atlas was a normal comet, and the appearance of anomalies was a statistical fluke combined with observational biases and cognitive effects. This argument went beyond the natural comet hypothesis by explicitly addressing why 3I/ATLAS seemed more mysterious than it should. The answer was human psychology and selection effects, not unusual physics. For 3I/ATLAS, dozens if not hundreds of distinct measurements were made, purely by statistics. Several should show unusual values even if the comet was entirely typical. The human tendency is to pay more attention to the unusual measurements than the normal ones. We remember the weird results and forget the 20 boring ones. This creates an illusion that anomalies are more common than they really are. This is called the quote 3 in science. Unusual results get published and discussed. Normal results often don't get published because they're not interesting. This creates literature bias where the published record overrepresents anomalous findings. For 3I/ATLAS, the papers discussing puzzling observations got attention. The many measurements that were perfectly normal didn't generate papers and weren't prominently discussed. The statistical fluke argument suggested that if you compiled all observations, normal and anomalous, and assessed them statistically, you'd find the anomaly rate was exactly what random chance predicts. This argument was difficult to rebut rigorously because it required comprehensive meta-analysis that no one had performed. Gathering all observations, published and unpublished, from all groups and analysing them collectively would be a major undertaking. The few researchers who tried to assess this question reached mixed conclusions. Some found that the number of anomalies was indeed higher than random chance would predict. Others found marginal evidence either way. Part of the problem was defining what counted as an anomaly. If you use a strict statistical threshold, like 3 standard deviations from expected values, very few observations qualified. If you use a looser definition, many did. The choice of threshold significantly affected conclusions, and there was no objective way to choose the right threshold without assuming the answer you were trying to determine. Another aspect of the statistical fluke argument involved publication bias. Researchers who found unusual results had more motivation to publish than those who found normal results. This could create the appearance of widespread anomalies even if most data was boring. This effect is well documented in other fields. Medical studies that find significant drug effects are more likely to be published than those that find no effect, creating literature bias. For 3I/ATLAS, if teams that measured normal properties didn't bother to publish while teams that measured anomalies did publish enthusiastically, the literature would give a skewed impression. Attempts were made to look for this bias by contacting observers and asking about unpublished measurements. Some teams did report having data showing normal properties that they hadn't published because it seemed uninteresting. But the magnitude of this effect was hard to quantify. Even if some normal data was unpublished, the published anomalies might still represent real unusual properties. The statistical fluke argument also pointed to cognitive biases. Humans are pattern-seeking creatures. We see patterns even in random noise. We remember coincidences and forget the many times things happen independently. For 3I/ATLAS, perhaps researchers were seeing patterns in noisy data that weren't really there. The brightness variations might be random fluctuations that observers were interpreting as meaningful patterns. This interpretation was perhaps the most frustrating of all because it suggested that more data wouldn't necessarily resolve the mystery. If the mystery was partly statistical artifact, more observations might just create more apparent anomalies. The only way to test this interpretation would be observing many more interstellar comets and seeing if they all appeared as mysterious as 3I/ATLAS, or if it was an outlier. Future surveys would eventually provide this data, but it would take years or decades. In the meantime, the statistical fluke argument served as a caution against overinterpreting ambiguous data, and a reminder that sometimes the most interesting explanation is that there's nothing particularly interesting happening. Rather than choosing one hypothesis, some researchers argued that 3I/ATLAS's behaviour resulted from multiple effects operating simultaneously, creating complexity that no single explanation could capture. This combined complexity explanation suggested that the comet had several unusual properties: somewhat extreme shape, heterogeneous composition, active fragmentation, and unusual rotation state, all happening at once. None of these properties individually would be extraordinary. Elongated comets exist. Compositionally heterogeneous comets exist. Fragmenting comets are common. Complex rotation occurs. But having them all in one object, combined with observational challenges from the comet's distance and faintness, created the appearance of deep mystery. The brightness variations reflected rotation of an elongated heterogeneous nucleus that was also fragmenting. Each process contributed to the light curve in overlapping ways that made separating them difficult. The shape changes were partly real from fragmentation, partly apparent from changing viewing geometry and activity patterns. Different measurement techniques were sensitive to different aspects of the complex shape distribution, explaining why they gave inconsistent results. The spectroscopic confusion arose from spatially and temporally variable composition as fragmentation exposed interior material, combined with measurement difficulties and perhaps genuinely unusual bulk chemistry. The trajectory oddities reflected outgassing from the fragmenting, rotating asymmetric nucleus in ways that simple models couldn't capture, but that more complex models could potentially reproduce. This multi-causal explanation had appeal because it acknowledged the data's complexity without requiring any single dramatic anomaly. It was the Occam's razor approach. Don't multiply entities beyond necessity, but do allow as many as are necessary. The challenge was that testing the combined complexity explanation required very sophisticated models that included all the proposed effects and their interactions. Such models existed in principle. You could build computer simulations of fragmenting, rotating, sublimating nuclei with heterogeneous compositions and realistic shapes, then predict their observable properties. This was unsatisfying in the way that complex explanations always are. We want nature to be simple, to follow clean principles that explain observations parsimoniously. Invoking multiple simultaneous effects feels like giving up on that ideal. But perhaps that ideal was inappropriate for a system as inherently complex as a comet. These objects are not simple. They have complicated histories, diverse compositions, irregular shapes, chaotic dynamics. Expecting them to behave simply might be naive. The combined complexity view suggested that 3i/Atlas was teaching us humility, teaching that not every natural phenomenon fits into neat categories, that some things genuinely require complex explanations because they result from complex causes. This interpretation wouldn't satisfy those looking for a dramatic revelation about the comet's nature. There was no single quote to what 3i/Atlas was, just a recognition that it was many things simultaneously. But perhaps that was the deepest lesson, that nature is richer and more multifaceted than our explanatory frameworks typically acknowledge, and that understanding sometimes means accepting complexity rather than reducing it. The combined complexity explanation thus served as a philosophical statement as much as a scientific hypothesis, a statement about the limits of simple explanations and the value of embracing reality's messiness. Whether this represented mature wisdom or intellectual surrender remained a matter of perspective and perhaps personal temperament. Different researchers reacted to 3i/Atlas's complexity differently, based on their tolerance for ambiguity and their preferences for simple versus comprehensive explanations. A fundamental limitation in understanding 3i/ATLAS was simple. We couldn't see it well enough to resolve many of the questions that observations raised. The comet's nucleus was roughly 3 kilometers across at a distance that varied but was typically 1 to 2 astronomical units from Earth. At 1 astronomical unit, 150 million kilometers, a 3-kilometer object subtends an angle of roughly 0.004 arc-seconds. This is far below the resolution limit of even the largest ground-based telescopes. Earth's atmosphere blurs images to roughly 0.5 to 1 arc-second resolution even at the best sites. Adaptive optics can improve this to perhaps 0.05 arc-seconds in ideal conditions. Spacecraft flybys could provide the needed resolution, but would require launching a mission years in advance with uncertain target trajectory. The warning time between discovery and perihelion passage was only months, far too short for spacecraft mission development. This resolution barrier meant that many questions about 3I/ATLAS's structure simply couldn't be answered with available technology. Was the nucleus a single body or multiple fragments? Was the shape smooth or irregular at small scales? How was ice distributed? All these questions required directly imaging the nucleus at resolutions current instruments couldn't achieve. The limitations extended beyond imaging. Spectroscopy also suffered from resolution limits. Spatially resolved spectroscopy, measuring composition at different locations on the nucleus, required imaging resolution we didn't have. We could measure average composition of the whole coma, but we couldn't determine if different parts of the nucleus had different compositions. Heterogeneity that might explain some puzzling observations remained unmeasurable. The resolution barrier wasn't just about instruments, it was also about timing. The comet was bright enough for detailed study only during a limited window around perihelion. Before and after that window, it was too faint. This gave observers perhaps 6 months of useful observation time total. Many telescopes and instruments that might have contributed valuable data couldn't be scheduled during that crucial window due to competing demands. Hubble Space Telescope time is precious and competitive. Getting significant allocations for 3I/ATLAS was difficult because other science programs had priority. The observations that were made provided useful data but left many questions unanswered. The resolution barrier thus created a fundamental epistemological limit. There were things we wanted to know about 3I/Atlas that simply couldn't be known with existing technology and the observing time available. This wasn't a temporary problem that more analysis could solve. Better analysis of bad data doesn't create good data. The information just wasn't in the observations at the level of detail needed. This realization was frustrating for researchers who felt they were close to answering key questions if only they could see a bit more clearly, measure a bit more precisely. But it was also a sobering reminder of human limitations. We can only know what our instruments can measure. Objects that don't cooperate by being large, close, and bright remain partially mysterious regardless of our efforts. The resolution barrier meant that some mysteries of 3I/ATLAS would likely remain unsolved until future technology or serendipitous closer approaches by similar objects provided better data. This was unsatisfying but realistic. Science often proceeds in fits and starts, with periods where observations outpace understanding, and other periods where understanding awaits better observations. 3I/Atlas fell into that latter category, an object whose full characterization awaited instruments that didn't yet exist, and observation opportunities that might not recur for decades. Beyond resolution, another fundamental limitation was signal-to-noise ratio. The comet was simply faint, and measuring faint objects accurately is inherently challenging. At its peak brightness around perihelion, 3I/Atlas reached roughly 9th magnitude. Visible through small telescopes but far fainter than the unaided eye can see. For spectroscopy and other specialized observations requiring dispersing light or dividing it into multiple channels, the effective brightness was even fainter, often 13th or 14th magnitude. At these faint levels, photon statistics become limiting. The number of photons collected from the comet in a typical exposure might be only hundreds or thousands from each part of the spectrum. With such limited photon counts, random statistical fluctuations, noise, become significant compared to the signal you're trying to measure. The signal-to-noise ratio, often abbreviated SNR, determines measurement precision. If you're collecting 1,000 photons, the statistical uncertainty is the square root of 1,000, roughly 30 photons, giving SNR of about 30 to 1. An SNR of 30 means you can measure relative intensities to roughly 3% precision at best. Subtle spectroscopic features or small brightness variations might be below this precision threshold. For fainter measurements with fewer photons, SNR gets worse. An observation collecting 100 photons has SNR of 10 and precision of only 10%. Many observations of 3I/Atlas were in this regime or worse. The spectroscopic features being analysed were often only marginally above the noise floor. This created ambiguity in interpretation. A small peak in a spectrum might be a real emission line, or might be a random noise fluctuation. Without higher SNR, distinguishing these possibilities was difficult. Different analysis techniques made different assumptions about noise properties and about what constituted a quote 5 signal versus noise. This led different teams analysing the same data to identify different features as significant. Papers were published claiming detection of specific spectral lines that other teams looking at the same spectra couldn't confirm. The disagreement wasn't about honesty or competence, but about where to draw the line between signal and noise with marginal data. The signal-to-noise challenge affected time-resolved observations particularly severely. To see how things changed with time required taking many observations, each necessarily shorter exposure than if you could integrate all the light into a single long exposure. These shorter exposures had worse SNR individually. Tracking brightness variations or spectroscopic changes over time required extracting small signals from noisy data at each epoch. Future observations of brighter interstellar comets or closer approaches would provide better SNR and potentially resolve some ambiguities. But for 3I/ATLAS specifically, the SNR of available data was what it was and couldn't be improved after the fact. Sophisticated analysis could squeeze more information from marginal data, but couldn't create information that wasn't captured in the first place. There were limits to what could be extracted from noisy measurements. The signal-to-noise challenge thus joined the resolution barrier as fundamental observational limitations that prevented definitive characterization of 3I/Atlas, regardless of how carefully astronomers analysed the data. Beyond random noise, systematic errors presented another layer of observational difficulty that complicated understanding 3I/ATLAS. Systematic errors are biases that affect measurements in consistent ways rather than randomly. They make measurements systematically too high or too low by amounts that don't average out with more observations. For astronomical observations, systematic errors arise from many sources: imperfect calibration of instruments, atmospheric effects that aren't perfectly corrected, scattered light from bright objects nearby, time-variable detector sensitivity. Each of these can introduce biases into measurements that are difficult to detect and correct without independent verification methods. For 3I/Atlas, several systematic error sources were particularly problematic. One was background contamination that varied with time and position. The zodiacal light background changes as Earth moves in its orbit, and as the line of sight to the target passes through different parts of the zodiacal dust cloud. Perfectly subtracting this variable background is difficult. If background subtraction was slightly incorrect, it would bias brightness measurements. Worse, the bias might be different at different times, creating apparent variability that was actually measurement artifact. Researchers tried to account for this by carefully modelling backgrounds and using multiple reference regions in each image, but uncertainties remained about whether background was being subtracted accurately. Another systematic error source was atmospheric extinction for ground-based observations. Earth's atmosphere absorbs and scatters light, making objects appear dimmer than they actually are. The amount of extinction depends on atmospheric conditions and on the elevation angle of the observation. Careful calibration using standard stars observed through similar atmospheric paths can correct for this. Spectroscopic observations faced additional systematic errors. Wavelength calibration determines which pixels in the detector correspond to which wavelengths of light. Small errors in wavelength calibration shift spectral features to wrong wavelengths. If features appeared at slightly unexpected wavelengths, Was this because the source was moving with a Doppler shift, or because wavelength calibration was imperfect? Distinguishing these required very accurate calibration. Difficult to achieve consistently. Different spectrographs on different telescopes had different systematic properties. Comparing spectra from multiple instruments required understanding these systematics well enough to know if differences reflected real variations in the target or just instrumental differences. This comparison was often difficult. Papers reporting spectroscopic observations sometimes gave inconsistent results, partly because instrumental systematics were being interpreted as real signals. Flat fielding, the process of correcting for pixel-to-pixel sensitivity variations in detectors, introduced additional potential systematics. Imperfect flat field corrections left residual patterns in images that could be mistaken for real structure. Some reports of structure in 3I/Atlas's Comet might have been detector artifacts rather than real features. Without independent verification, distinguishing these cases was challenging. The time-variable nature of many systematics made them particularly pernicious. If an error source varied randomly from one observation to the next, it would average out in time series data. But if it varied systematically, perhaps with temperature or with time of night, it could create false patterns. Researchers attempted to identify and mitigate systematics through various techniques, comparing multiple instruments, using multiple analysis methods, looking for internal consistency checks. This made distinguishing robust conclusions from tentative suggestions challenging and contributed to the proliferation of different interpretations of the same observations. Understanding observations of 3I/ATLAS required comparing them with theoretical predictions, but the models available for predicting cometary behavior had their own significant limitations that added uncertainty. Cometary physics is complex, involving thermal processes, fluid dynamics, structural mechanics, chemistry, radiation transport and orbital dynamics all coupled together. No single model captures all these processes at once with high fidelity. Instead, researchers use simplified models that approximate reality well enough to make useful predictions, while remaining computationally tractable and conceptually manageable. For thermal modelling, standard approaches treat the nucleus as a porous sphere with heat, conducting inward and ice sublimating according to temperature-dependent vapor pressure relations. These models work reasonably well for many comets, but make assumptions: spherical symmetry, homogeneous composition, simplified pore structure, local thermodynamic equilibrium. For 3I/Atlas, if the nucleus was highly elongated, fragmenting, compositionally heterogeneous, and possibly not in thermal equilibrium, these assumptions all became questionable. More sophisticated models relaxing some assumptions could be constructed, but they required specifying many parameters about the detailed nuclear structure that weren't measured. Laboratory studies of ice properties exist, but typically use pure ices at conditions not quite matching cometary environments. How complex mixtures of ices and dust behave under realistic cometary conditions isn't fully determined experimentally. Models made educated guesses based on extrapolation from laboratory data, but the material properties of actual comet nuclei remained uncertain by factors of several to 10. This meant predictions about when thermal stress would cause cracking, how tidal forces would deform the nucleus, or how fragmentation would proceed were all uncertain within wide ranges. Spectroscopic models predicting emission line strengths from cometary comas involved complex atomic and molecular physics, fluorescence processes, collisional excitation, photodissociation, all in non-equilibrium conditions. State-of-the-art models captured much of this physics but still made simplifications. Some molecular energy levels might be approximated, some collision cross-sections poorly known, some chemical reaction rates uncertain. The result was that predicted spectra matched observed spectra at about the 20 to 30% level typically. Good enough for rough composition estimates, not good enough to definitively identify weak features or measure precise abundance ratios. For 3I/Atlas's unusual spectroscopic signatures, model limitations made interpretation difficult. Were unidentified features real but from molecules not in the model? Or were they artifacts from model approximations? Orbital dynamics models predicting trajectories with non-gravitational forces had their own parameter uncertainties. The magnitude and direction of outgassing forces depend on activity distribution, rotation state, nucleus shape, all of which were imperfectly known. Models typically parameterized these unknowns and adjusted parameters to fit observations. But different parameter choices could fit equally well, meaning the trajectory data couldn't uniquely determine the physical configuration. The theoretical model limitations meant that even with perfect observations, extracting physical properties of the comet required interpretation through imperfect models that introduced additional uncertainty. Combined with observational limitations, this created a situation where observations couldn't decisively test models, and models couldn't definitively interpret observations. Theory and observation remained loosely coupled rather than tightly constraining each other. Some researchers hoped that better models would eventually resolve 3I/ATLAS's mysteries by correctly interpreting the existing observations. Others suspected that model improvements alone wouldn't suffice without better observations. This chicken and egg problem, needing better models to interpret observations but needing better observations to develop better models, is common in astronomy, but was particularly acute for 3I/ATLAS. The theoretical limitations thus joined the observational limitations as fundamental barriers to understanding that prevented reaching confident conclusions despite significant effort by many researchers. A different kind of limitation arose from trying to compare 3I/Atlas with other comets to determine how unusual it really was. The challenge of making meaningful comparisons across diverse observation methods and object properties. Every comet is unique, observed under different circumstances with different instruments by different teams. Making apples-to-apples comparisons is difficult when the observations themselves are heterogeneous. 3I/Atlas was observed primarily during 2024 with instruments and techniques available then. Solar system comets in archives were observed over decades with evolving instrumentation. Comparing brightness behavior required accounting for different photometric systems, different filter sets, different calibration methods across observations spanning years or decades. Spectroscopic comparisons faced even greater challenges. Spectrographs have different wavelength coverage, resolution, sensitivity. A spectral feature visible in one dataset might be outside the wavelength range or below the detection threshold of another. Compositional comparisons required standardizing how abundances were derived from spectra. Different teams used different methods, different molecular models, different assumptions about excitation conditions, different ways of converting line strengths to abundances. Published abundances for the same comet from different papers sometimes differed by factors of 2 or more due to these methodological differences. Comparing 3I/ATLAS to other comets required accounting for these systematic uncertainties. Shape comparisons faced the problem that many comets didn't have well-determined shapes. Size and rotation period were often known, but axis ratios and detailed morphology were uncertain for all but a few well-studied targets. Saying 3I/Atlas was, quote, 6, required knowing the distribution of elongations in other comets. But that distribution was poorly characterized because most comets lacked the high-quality data needed to measure elongation. The sample of well-characterized comets was small and biased toward bright, nearby objects that were easiest to study. Faint distant comets like 3I/ATLAS for most of its apparition were underrepresented. This selection bias made it difficult to know whether 3I/Atlas was truly unusual or just appeared so because most comets weren't studied carefully enough to reveal similar complexity. Models existed for how properties should scale with solar distance, but these models had uncertainties and might not apply equally to all comets. The literature on solar system comets, accumulated over decades, contained observations of varying quality, using diverse and often poorly documented methods. Extracting consistent comparisons from this heterogeneous literature required careful meta-analysis that few had attempted comprehensively. Individual papers compared 3I/ATLAS to small samples of other comets in specific properties. But a systematic comparison across all properties and a large representative sample of comets was lacking. Without such comprehensive comparison, claims about how unusual 3I/Atlas was relied partly on subjective impressions from researchers familiar with comets generally but not necessarily with quantitative statistical assessments. The comparability challenge meant that even if 3I/Atlas had been perfectly observed, determining how it fit into the population of comets would remain difficult due to incomplete knowledge of that population. This limitation was more surmountable than some others. Future surveys will characterize more comets more thoroughly, building up statistics. Eventually we may be able to place 3I/ATLAS in proper statistical context. But for now, in 2024 and the years immediately following, that context was lacking. We knew 3I/Atlas was somehow unusual, but couldn't quantify precisely how unusual in most properties. This uncertainty about context compounded all the other uncertainties. Not only did we not fully understand 3I/Atlas itself, we didn't fully understand how typical or atypical it was, making interpretation of its properties even more ambiguous. One of the most unexpected and philosophically interesting aspects of studying 3I/ATLAS was the phenomenon where accumulating more observations didn't clarify the picture, but instead made it more confused. Normally in science, more data is better. Initial observations might be ambiguous, but additional measurements reduce uncertainty, narrow the range of viable hypotheses, and guide convergence toward truth. For 3I/ATLAS, this pattern didn't hold in the expected way. Instead of converging, interpretations seemed to diverge as more observations accumulated. This phenomenon of rational disagreement, where equally intelligent and informed people reach different conclusions from the same data, is well known in philosophy of science but not always acknowledged in practice. For 3I/Atlas, it meant that even consensus conferences and workshops didn't produce consensus. People acknowledged each other's perspectives but didn't converge to common views. The situation was exacerbated by normal scientific sociology. Researchers invested significant effort in particular interpretations naturally became advocates for those views, perhaps overweighting confirming evidence and underweighting contradicting evidence. Publication incentives favoured novel claims over incremental refinements. Papers claiming unusual features got more attention than papers finding normal properties. This created pressure to emphasise anomalies even when evidence was marginal. Peer review should have balanced this. But reviewers had their own biases and faced the same interpretative ambiguities as authors. Different reviewers reached different conclusions about whether claims were adequately supported. The result was a published literature that didn't converge but sprawled, with multiple contradictory claims coexisting and no clear mechanism for resolving disagreements. Some philosophers of science have studied cases where scientific controversies persist despite accumulating evidence. The factors they've identified, ambiguous data, theory under determination, systematic uncertainties, social dynamics, all applied to 3I/ATLAS. The case became an interesting example for science studies scholars of how scientific uncertainty can persist and even grow despite intensive investigation. For the astronomers involved, it was frustrating. They were working hard, making good observations, analysing carefully. But the pieces weren't coming together into a coherent picture. Some wondered if they were missing something obvious, if future researchers would look back and see a simple explanation they'd overlooked. Others suspected the confusion was inherent to the problem, not a failure of insight. The lesson that more data doesn't automatically mean more understanding was humbling. It suggested that some phenomena, some questions, resist investigation not because we're not trying hard enough, but because the problem's structure makes clear answers difficult. This realization didn't stop people from continuing to study 3I/ATLAS, or from planning observations of future interstellar comets, but it tempered expectations about how quickly mysteries would be resolved. A recurring theme throughout the 3I/Atlas investigation was how strongly expectations shaped interpretation of observations, often in ways researchers didn't fully recognize. Scientists like to think they approach data objectively, letting observations guide conclusions without preconception, but in practice, prior expectations strongly influence what we see, how we interpret it, and what conclusions we draw. For 3I/Atlas, expectations operated at multiple levels. The most basic was the expectation that it would be a comet, behaving like comets do. This expectation was reasonable given the hyperbolic orbit and early detections of Comet and tail. But it created a framework where observations were interpreted through cometary physics even when they might not fit well. Alternative interpretations that perhaps 3I/Atlas wasn't entirely like typical comets were considered but tended to be dismissed or marginalized unless evidence was overwhelming. For 3I/ATLAS, some researchers wondered if this bias might be hiding the true nature of the object. Perhaps it was more unusual than being acknowledged because the community was committed to finding cometary explanations. Another layer of expectation came from the previous interstellar objects. 1I/Oumuamua had been so weird, possibly not a comet at all, that expectations for 3I/Atlas included the possibility of finding something equally strange. This created opposite bias. Heightened attention to anomalies and perhaps overinterpretation of marginal signals as evidence of exotic properties. The tension between these biases, conservatism toward normal interpretations versus excitement about finding something weird, pulled in opposite directions and likely contributed to the diversity of interpretations. Expectations also operated in how observations were designed. Observers expected certain behaviors based on cometary models and designed observations to test those expectations. This is good scientific practice. Theory guides observation, but it can create blind spots. If you're not looking for something because you don't expect it, you might miss it even if it's there. Some properties of 3I/Atlas might have gone unobserved simply because no one thought to look for them. The observation time was limited, and choices had to be made about what to observe. Those choices reflected priorities based on expected importance, which reflected underlying assumptions about what mattered and what the comet would be like. In retrospect, it's easy to wish certain additional observations had been made, but in real time, with limited resources and incomplete information, observers made reasonable choices based on what seemed most likely to be useful. Cognitive psychology research on confirmation bias shows that people tend to notice and remember evidence consistent with their beliefs, while overlooking or forgetting contradictory evidence. Scientists are trained to counter this bias through systematic method, hypothesis testing, peer review, replication. But the bias isn't eliminated, just reduced. For 3I/Atlas, researchers with different theoretical perspectives reported emphasizing different subsets of observations in their analyses. Those who thought fragmentation was key focused on observations supporting that view. Those who thought composition was anomalous emphasized spectroscopic results. Each group's papers highlighted evidence for their interpretation, while downplaying contradictory evidence or explaining it away. This wasn't dishonesty, but natural human tendency to build cases for views we find compelling. The scientific community as a whole is supposed to correct for individual biases through diversity of perspectives. No single person is objective, but the community can approach objectivity through dialectic between competing views. For 3I/Atlas, this collective process was ongoing but hadn't reached resolution. Different perspectives were being articulated and debated, but convergence hadn't occurred. Expectations also shaped interpretation at the level of specific measurements. When analysing marginal signals, researchers' prior beliefs about what was plausible influenced how they distinguish signal from noise. If you expect to find a particular spectral feature, you're more likely to identify a marginal peak at the appropriate wavelength as that feature rather than as noise. Different expectations lead to different identifications from the same data. This isn't about manipulating data dishonestly. It's about where to set thresholds in ambiguous cases. Reasonable people can disagree on these thresholds based on their background knowledge and expectations. The role of expectations in shaping scientific investigation is unavoidable. We can't approach observation without any conceptual framework or assumptions. Pure empiricism, observing with absolutely no theoretical preconceptions, isn't possible in practice. The question is whether expectations are helping or hindering understanding. Ideally, they should guide investigation productively while remaining flexible enough to update when observations demand it. For 3I/Atlas, different researchers would assess differently whether community expectations were functioning well. Some thought the field was appropriately cautious, requiring strong evidence before accepting unusual claims. Others thought it was too conservative, dismissing anomalies that deserved more serious consideration. These meta-level disagreements about how science should be done compounded the object-level disagreements about what 3I/ATLAS actually was. The lesson was that scientific investigation is a deeply human process, influenced by psychological and sociological factors as much as by pure logic and evidence. Acknowledging this doesn't undermine science, but makes it more realistic and perhaps more effective. 3I/Atlas highlighted fundamental limits to what can be learned about distant objects through remote observation, no matter how sophisticated our instruments become. All astronomical observation is remote. We can't touch the objects we study, can't visit them, can't manipulate them experimentally. We learn through electromagnetic radiation they emit or reflect. This remote nature imposes irreducible limitations. Some properties simply can't be determined from light alone without additional assumptions or indirect inference. For 3I/Atlas, the internal structure was fundamentally unknowable through remote observation. We could infer properties from how the object behaved, but we couldn't directly measure what was inside. Was the nucleus a monolithic block of ice, a loose rubble pile, layered like an onion? These different structures might behave similarly enough that observations couldn't distinguish them. The inverse problem, inferring causes from effects, is inherently ambiguous. Multiple different internal configurations could produce the same external observations within measurement uncertainties. Mathematically, the space of possible models that fit observations is often large or even infinite. Additional constraints from physical plausibility narrow this space, but rarely to a unique solution. For 3I/Atlas's shape evolution, we could propose many different structural models that would produce similar observed changes. Without direct knowledge of material properties and structural arrangement, choosing between these models required assumptions. Those assumptions might be reasonable, based on knowledge of other comets and ice physics. But they remained assumptions, not direct measurements. The time domain provided some additional constraints. How things changed over time revealed dynamics that constrained models. But the observation temporal sampling was limited, with gaps during bad weather, scheduling conflicts, and instrument downtime. Between observations, we didn't know what happened. Changes might have occurred that went unobserved because they happened when no one was looking. This temporal limitation meant that we might have missed key events, fragmentation moments, outbursts, structural changes. What we observed was a sparse sampling of continuous evolution. Spatial limitations compounded temporal ones. We couldn't observe different parts of the nucleus separately. Everything was averaged together in the integrated light received. Spatial heterogeneity, different properties in different locations, could produce time-variable signals as rotation brought different regions into view. But distinguishing this from other time-variable processes required assumptions about rotation and surface distribution. The wavelength coverage of observations, while extensive, wasn't complete. Some parts of the electromagnetic spectrum were unobserved due to atmospheric absorption or instrumental limitations. Information in those unobserved wavelengths was inaccessible. Perhaps key spectral features existed in the far infrared or far ultraviolet that would have clarified composition, but we couldn't observe those regions. The fundamental detection threshold also mattered. Phenomena that produce signals below detection limits would be invisible regardless of how long we observed. Subtle processes, minor components, weak emissions, all might exist but be undetectable with current technology. The absence of detection didn't prove absence, just that if present, the signal was below threshold. These limitations weren't failures of the investigators or the instruments. They were fundamental constraints on remote observation that better telescopes and longer observation times could ameliorate but not eliminate. Some information simply isn't contained in the electromagnetic radiation we can collect. No amount of clever analysis extracts information that isn't there. The lesson from 3I/ATLAS was humility about the limits of astronomical knowledge. We can learn much through remote observation, but we can't learn everything. Some questions about distant objects will remain unanswered, not because we haven't tried hard enough, but because they can't be answered from light curves and spectra alone. This realization was important for setting realistic expectations about future interstellar object studies. Even with much better instruments, some mysteries will likely persist. The ultimate solution would be spacecraft missions to interstellar visitors, allowing direct in situ study. But such missions face enormous challenges in rapid targeting and interception. Until those challenges are overcome, if they ever are, our knowledge of interstellar objects will remain limited by the irreducible constraints of remote observation. For 3I/ATLAS specifically, this meant that many questions raised by its unusual behaviour would likely never be definitively answered. The object was gone, and the observational window had closed. Future similar objects might allow testing hypotheses developed from 3I/ATLAS, but the specific mysteries of this particular comet would remain partly unsolved. A permanent reminder of the limits of what we can know about the cosmos from our distant vantage point. While frustrating for researchers seeking clear answers, the persistent mysteries of 3I/ATLAS raised interesting questions about the value of unresolved scientific puzzles and what they contribute to knowledge. Traditionally, science is viewed as answering questions, solving puzzles, resolving uncertainties. Successful science produces understanding where previously there was ignorance. By this metric, the 3I/ATLAS investigation might seem unsuccessful. After intensive study, many questions remained unanswered. The comet's true nature stayed mysterious. But there's another way to view scientific progress, not just as producing answers, but as refining questions, identifying what we don't know, and clarifying the boundaries of knowledge. This pattern is common in science history. Major advances often follow from recognizing what we don't understand. The anomalous orbit of Mercury preceded general relativity. Unexplained spectral lines led to quantum mechanics. 3I/ATLAS might not be as historically significant as those examples, but it followed the same pattern. Anomalies revealing inadequacies in current frameworks and motivating improved understanding. The value of mystery extends beyond motivating research. It also serves epistemic functions, tempering overconfidence, encouraging humility, reminding us that nature is subtle and sometimes surprising. Scientific culture can trend towards certainty, toward claiming stronger understanding than evidence warrants. High-profile unsolved problems like 3I/ATLAS provide healthy correction to this trend. They remind the community and the public that science is ongoing, incomplete, provisional. Not everything is understood. Some things actively resist understanding despite significant effort. This message is important for science education and public understanding. Portraying science as a body of established facts makes it seem static and finished. Highlighting unsolved problems shows science as dynamic investigation. Students might be more engaged by mysteries than by settled knowledge. 3I/ATLAS's puzzles could inspire the next generation of cometry. astronomers precisely because they remain unsolved. The unresolved questions also have philosophical value. They raise interesting issues about the nature of explanation, the role of theory, the relationship between observation and understanding. Philosophers of science have analysed 3I/ATLAS as a case study in how scientific uncertainty persists and what that reveals about scientific methodology and reasoning. These meta-level insights might outlast whatever eventual resolution the empirical questions receive. Understanding how and why science gets stuck is as important as understanding specific natural phenomena. There's also aesthetic value in mystery. The universe would be less interesting if everything were explained. Part of the appeal of astronomy is contemplating vast unknowns. 3I/Atlas, with its unresolved puzzles, captures imagination in ways a fully understood object might not. The question, quote, invites ongoing engagement. This isn't to romanticize ignorance or suggest we shouldn't try to answer questions. Of course we should investigate, analyze, attempt to understand. But we can also appreciate mystery for its own sake. The balance between seeking answers and accepting uncertainty is delicate. Too much emphasis on answers leads to premature closure and false certainty. Too much acceptance of uncertainty leads to complacency and lack of progress. For 3I/ATLAS, the scientific community seemed to strike a reasonable balance. Continuing to analyse and interpret while acknowledging that some questions might remain open indefinitely. This mature relationship with uncertainty, neither demanding impossible certainty nor surrendering to complete agnosticism, might be the most valuable lesson the Comet offered. In practical terms, the unresolved questions influenced how future observations were planned. When the next interstellar comet was discovered, observers knew from 3I/Atlas what kinds of measurements were most valuable and where gaps existed. The specific observing strategies and instrument configurations used for subsequent objects reflected lessons learned from 3I/Atlas's ambiguities, so even without providing clear answers, 3I/Atlas contributed to improving how such objects are studied. Its mysteries became instructive rather than merely frustrating. The value of unresolved questions thus operated at multiple levels: scientific, educational, philosophical, aesthetic. Not all value in science comes from solving problems. Some comes from properly framing them, understanding their difficulty, and recognizing their significance. 3I/Atlas did these things well, even if it didn't provide the clean resolution that initially seemed possible. The disagreements and debates surrounding 3I/Atlas raised questions about how scientific controversy relates to scientific progress and whether the conflicts were productive or problematic. In popular imagination, science proceeds smoothly from question to answer through objective observation and logical reasoning. Scientists gather data, analyze it, and reach consensus about what it means. Reality is messier. Scientists often disagree, sometimes fundamentally, about how to interpret observations. These disagreements can persist for years or decades. For 3I/Atlas, the disagreements were substantial. Different research groups reached different conclusions about basic properties. Was the shape changing or not? Was composition unusual or normal? Was fragmentation occurring or not? Papers with contradictory claims were published in peer-reviewed journals. Conference presentations showed competing interpretations. The casual observer might wonder how scientists looking at the same object could disagree so strongly. This situation can seem problematic. If science can't reach consensus about a specific observable phenomenon, how can we trust scientific claims generally? But the philosophy and history of science suggest that such controversies are normal and often productive. Disagreement drives investigation. If everyone agreed immediately, there would be no motivation for further inquiry. The 3I/Atlas controversies motivated continued observation and analysis. Different groups worked to support their interpretations and challenge competing ones. This competitive process pushed the field forward. The disagreements also reflected honest assessment of genuinely ambiguous evidence. The data was marginal in key respects. Reasonable people could interpret it differently. This wasn't failure of the scientific method, but the method working as designed. Multiple researchers independently analysing data and reporting results, with disagreements resolved through continued investigation. The timescale for resolution was slower than ideal, because the object was gone and new observations weren't possible. For ongoing phenomena, controversies typically resolve faster, because new data can test competing predictions. The controversy had some negative aspects. It might have confused public understanding of what was known versus uncertain about 3I/ATLAS. It might have created impression that astronomers didn't know what they were doing. Some researchers worried about this reputational effect. Visible disagreement might undermine confidence in astronomy, or science generally. But others argued this was healthy transparency. Showing the messy reality of scientific investigation was more honest than presenting false consensus. The public is capable of understanding that scientists can disagree in good faith while all trying to get at truth. Pretending controversies don't exist would be the real trustbreaker. Within the scientific community, the controversy had mixed effects. It created some interpersonal tension, as researchers invested in different views sometimes clashed in debates or peer review. But it also sparked creativity. Having to defend views against criticism forced sharpening arguments, considering alternative explanations, looking for additional evidence. The process of controversy can be intellectually productive even when it's socially uncomfortable. The clash of ideas generates insights that wouldn't emerge from individual work alone. Historical examples support this. Many major scientific advances emerge from controversies. The nature of light, the existence of atoms, continental drift, all involve substantial disagreement before resolution. The controversies weren't obstacles to progress, but vehicles for it. Through debate and evidence accumulation, understanding advanced even when individuals didn't change their minds. For 3I/Atlas, the controversy was still ongoing as of late 2024. No clear resolution had emerged. Different interpretations coexisted. Whether future observations of similar objects would resolve the debates remained to be seen. Perhaps new data would clearly favour one interpretation. Or perhaps different interstellar comets would be different enough that 3I/Atlas's specific puzzles would remain unsettled. The sociology of how the controversy played out was interesting. Research groups tended to cluster around particular interpretations, with members collaborating and supporting each other's work. This tribalism can be problematic if it prevents engagement with contrary evidence. But it can also be productive if groups specialise in developing different approaches. The tension between these styles drives productive dialectic. Neither alone would be optimal. Together, they push field forward through creative exploration tempered by critical skepticism. For 3I/Atlas, having both conservative and speculative interpreters meant that all possibilities were being seriously considered, while wild speculation was being checked by demanding standards of evidence. The controversy thus served a useful function in the science, even while creating frustration for those seeking clear answers. Whether the specific disagreements about 3I/Atlas would be seen by future historians of science as important controversy or footnote depended on whether the issues resolved and with what implications. If it turned out 3I/Atlas was genuinely anomalous in ways that revealed new physics or chemistry, the controversy would be remembered as precursor to important discovery. If it was ultimately explained as normal cometary behaviour, the controversy might be forgotten as much ado about ambiguous data. Either way, the process of wrestling with uncertainty and disagreement was valuable for the participants in the field, contributing to scientific progress even without providing the tidy resolution that retrospective narratives often emphasize. The 3I/Atlas investigation raised deep questions about what it means to understand something scientifically, and whether understanding is binary or admits degrees. When astronomers said they didn't fully understand 3I/ATLAS, What exactly did they mean? There were things they knew with high confidence. It was an interstellar visitor, roughly 3 kilometers across, composed primarily of ice and dust. These facts constituted a level of understanding. They weren't complete ignorance about the object. But they weren't the detailed, comprehensive understanding that might be desired. The question was whether partial understanding counted as understanding at all, or whether understanding required answering all relevant questions. One philosophical view treats understanding as binary. Either you understand something, or you don't. By this standard, 3i/Atlas wasn't understood because key properties remained unknown and anomalies unexplained. But this seems too harsh. Surely knowing some things about an object constitutes some understanding, even if not complete understanding. An alternative view treats understanding as continuous spectrum from complete ignorance to complete knowledge. Most scientific understanding falls somewhere in the middle. By this standard, astronomers understood 3i/Atlas partially. They knew more than before observations, but less than ideally desired. This partial understanding had value. It constrained possibilities, ruled out some hypotheses, made predictions about future observations. It wasn't nothing. But it also had frustrating gaps. The core mysteries, why the shape might be changing, what caused the spectroscopic anomalies, what explained the trajectory oddities, remained largely unsolved. These gaps prevented confident claims about the comet's fundamental nature. Was it typical or exceptional? Natural or possibly artificial? Fragmenting or deforming? The inability to answer these questions meant that understanding, while partial, was incomplete in important ways. Philosophers of science distinguish between different types of understanding. There's phenomenological understanding, describing what happens without explaining why. And there's causal or mechanistic understanding, explaining the underlying processes producing observations. For 3i/Atlas, astronomers had decent phenomenological understanding. They could describe the observations. Brightness varied in particular ways. Spectra showed certain features. Shape appeared to evolve. But causal understanding was weaker. The mechanisms producing these phenomena remained uncertain. Multiple causal stories could be told, but which was correct wasn't clear. Scientific understanding typically aims for causal explanation, not just phenomenological description. Describing isn't enough. We want to explain. By this standard, understanding of 3i/Atlas was indeed incomplete. The observations were documented but not fully explained. Another aspect of understanding involves prediction. Do we understand something well enough to predict how it will behave in new circumstances? For 3i/ATLAS, predictive understanding was limited. Predicting its brightness at specific future times was possible only with large uncertainties. Predicting whether it would fragment further was speculative. This limited predictive power indicated incomplete understanding. If models couldn't reliably predict observations, they weren't capturing the relevant physics adequately. Yet another dimension of understanding is unification. Do we understand how this phenomenon fits with broader knowledge? Can we explain it using known principles, or does it require new physics? For 3i/Atlas, unification was partly achieved. The comet could be explained, at least roughly, using known cometary physics and chemistry. No new fundamental principles were needed, but the details didn't quite fit. Standard models required tweaking or special cases. This suggested either the comet was unusual within natural variation, or that standard models were incomplete. The inability to achieve clean unification indicated either gaps in understanding of this specific object or gaps in general understanding of cometary physics. Perhaps the most important aspect of understanding is the ability to answer why questions at progressively deeper levels. Why did 3i/Atlas behave as it did? Why that shape? Why that composition? Each answer should lead to deeper why questions. Why that formation environment? Why that ejection mechanism? Why that trajectory? For 3I/Atlas, the chain of why questions quickly reached levels where confident answers weren't available. Surface-level whys might be answerable. Deeper whys remained mysterious. This pattern is common in science. Understanding always bottoms out at some level where we can describe regularities but can't explain them more fundamentally. For 3I/ATLAS, that bottom was reached earlier than desired. The unexplained residue was larger than comfortable. The investigation thus highlighted that scientific understanding is complex, multi-dimensional, and often incomplete. We can understand some aspects while being ignorant of others. Recognizing this complexity might make us more careful about claims to understanding. Rather than binary, we understand this or we don't, we might specify what aspects are understood and what remain mysterious. For 3I/Atlas, we could say, we understand its gross properties and can describe its behavior, but we don't fully understand the mechanisms producing observed anomalies, or how typical versus exceptional it is in the population of interstellar objects. This more nuanced statement captures the state of knowledge better than simple, quote 12 or quote 13. The philosophical reflection on understanding thus suggested that 3I/Atlas investigation succeeded in advancing some dimensions of understanding while revealing limitations in others. This partial success was valuable even if unsatisfying to those seeking complete explanations. The persistent mysteries surrounding 3I/ATLAS raised a profound question. Should we expect natural phenomena to be ultimately comprehensible to human investigation? Or is mystery a permanent feature of our relationship with the cosmos? The scientific revolution was founded partly on the assumption that nature operates according to discoverable laws that human reason can understand. This assumption has been spectacularly validated by centuries of progress. We've explained phenomena that once seemed hopelessly mysterious: the motion of planets, the nature of light, the origin of species, the structure of matter. Science's track record suggests that with enough effort, most mysteries yield to investigation. But this optimistic view might not generalize to all phenomena at all scales. Perhaps some things genuinely resist full human comprehension, not temporarily, but permanently. For 3I/ATLAS, the question was whether its mysteries were temporary, pending better observations and models, or whether they reflected fundamental limits on what can be known about such objects. The temporary view said, of course it's mysterious now, we only observed it briefly with imperfect instruments. Future technology and future similar objects will resolve current puzzles. What seems irreducibly mysterious is just currently unsolved. This view maintained optimism about ultimate comprehensibility. Every mystery is just a puzzle waiting to be solved. There might be practical limits on what we can measure, but in principle, everything is knowable. The alternative view suggested that some phenomena might be inherently ambiguous, providing observations that cannot uniquely determine underlying reality, even with perfect measurements. For deeply complex, chaotic, or sensitive systems, full determination of past and internal states from external observations might be impossible in principle, not just in practice. Whether 3I/ATLAS fell into this category was debatable. It wasn't obviously a fundamentally unpredictable system, but its complexity might exceed what could be resolved from limited observations. If the nucleus was heterogeneous at small scales, with composition and structure varying in complicated ways, remote observations might never determine that small-scale structure completely. If fragmentation and sublimation involved chaotic processes depending sensitively on initial conditions, predicting or retroactively determining exact behavior might be impossible. These limits wouldn't reflect inadequate science, but fundamental properties of complex systems that make them partially unknowable to distant observers. This philosophical position embraces mystery as natural and permanent, rather than as temporary ignorance to be overcome. Some things might be fundamentally uncertain or unknowable. This isn't mysticism, but follows from physics and mathematics of complex systems. For individual scientists studying 3i/ATLAS, adopting this philosophical stance might provide psychological comfort. The failure to achieve complete understanding wasn't their failure but reflected the nature of reality. But it might also reduce motivation. If mysteries are permanent, why work so hard to solve them? Why not accept ignorance rather than struggling against it? The answer was that partial understanding is still valuable. Even if we can't know everything, knowing more is better than knowing less. Progressive refinement is worthwhile even without guarantee of reaching complete understanding. The 3i/Atlas investigation demonstrated this. Each observation, each analysis, added to knowledge even if it didn't resolve all questions. The accumulation was valuable. The philosophical stance toward mystery might vary among individual researchers based on temperament and worldview. Some needed to believe complete understanding was possible to stay motivated. Others found acceptance of mystery liberating. Both approaches could coexist productively in the scientific community. Those seeking complete understanding would push investigation forward. Those accepting mystery would prevent overreach and premature conclusions. For the broader public, the lesson that some things might remain mysterious could be either disappointing or fascinating. Some wanted science to answer all questions definitively. Others found ongoing mystery more engaging than settled knowledge. 3i/Atlas's persistent puzzles could thus serve educational purposes, showing that science deals with genuine mysteries that don't always resolve quickly or easily. This message countered the misconception that science is just a collection of established facts. It showed science as ongoing investigation of phenomena that sometimes resist easy explanation. Whether mystery was temporary or permanent for 3i/Atlas, specifically would only be known in retrospect, if ever. Future observations might clarify everything or might deepen the puzzles further. Either way, the investigation illustrated that mystery is at minimum a frequent state in scientific investigation, and perhaps a permanent feature of our relationship with complex natural phenomena. Embracing this possibility didn't mean abandoning investigation, but contextualizing it within realistic expectations about the limits of knowledge and the persistence of uncertainty. While initially frustrating, the ambiguity surrounding 3i/ATLAS could be appreciated for their own aesthetic and intellectual value, revealing a different kind of beauty than clear explanation provides. Scientific beauty is usually associated with elegant theories, simple explanations, harmonious relationships between phenomena. E=mc² has aesthetic appeal from its economy and power, but there's also beauty in complexity, in phenomena that resist simple explanation, in the richness of reality that exceeds our frameworks for understanding it. The process of wrestling with ambiguous data exercised skills valuable beyond this specific case: critical thinking, weighing evidence, recognizing limits of inference, maintaining multiple hypotheses simultaneously. These skills were perhaps more important than any specific facts about 3i/ATLAS. The Comet became a vehicle for developing intellectual capabilities that transferred to other contexts. There was also aesthetic pleasure in the investigation itself, independent of whether it reached conclusions. The process of careful observation, creative interpretation, collaborative debate had its own beauty. Like a complex chess game beautiful for the interplay of strategies even if the outcome is draw, the 3i/Atlas investigation was beautiful for the intellectual moves it inspired. The ambiguity forced creativity. With clear data pointing to obvious conclusions, analysis would be straightforward but perhaps boring. Ambiguous data required innovation in interpretation. Researchers proposed novel ideas about cometary behavior, developed new analysis techniques, extended models in creative ways. This creativity was stimulated by ambiguity and might not have emerged from simpler cases. The competing interpretations created an intellectual landscape rich with debate and dialectic. Conference presentations showed diverse perspectives. Papers argued for different views. This plurality of thought had aesthetic appeal. like a conversation where multiple voices contribute without any dominating. The polyphony was more interesting than a monotone would be. The ambiguity also created connection to historical mysteries. 3i/Atlas joined a tradition of astronomical puzzles that engaged observers across generations. What are comets? What causes zodiacal light? What powers quasars? Some of these mysteries were eventually solved. Others remained open for decades or centuries. 3i/Atlas's place in this tradition connected current research to long history of astronomical investigation. There was humility in ambiguity as well. The inability to definitively explain 3i/Atlas reminded us that human knowledge is limited and nature is vast. This humility has its own austere beauty, the recognition that we are small and universe is large, that our understanding is partial and reality is rich. Eastern aesthetic traditions, particularly in Japanese culture, recognize beauty in incompleteness and imperfection. Wabi-sabi embraces the impermanent, incomplete and ambiguous as sources of aesthetic value. By wabi-sabi standards, 3i/Atlas's unresolved mysteries made it more beautiful than a fully explained object would be. The gaps and uncertainties were features, not bugs. This aesthetic wasn't universally shared. Western intellectual traditions often value completeness and certainty over ambiguity. Scientists trained in these traditions might find the lack of resolution frustrating rather than beautiful. But there was value in considering alternative aesthetic frameworks that found beauty in different places than traditional scientific aesthetics emphasized. The ambiguity also opened 3i/ATLAS to multiple levels of engagement. Specialists could debate technical details. Educated amateurs could appreciate the broad questions without needing complete understanding. Children could be told that mysterious visitor came from the stars and we're still trying to understand it. The mystery was accessible and engaging across expertise levels. A fully explained technical phenomenon might be beautiful to specialists but opaque to others. Ambiguous mystery could be appreciated by anyone who valued questions as much as answers. There was narrative beauty in the story of 3i/Atlas investigation. Initial straightforward appearance giving way to deeper mysteries, accumulating observations that deepened rather than resolved puzzles, diverse interpretations competing without clear winner. This narrative arc was engaging in ways a simple, we observed it, we understood its story wouldn't be. Good stories have tension and ambiguity. 3i/Atlas provided both. For those working on 3i/Atlas, the aesthetic appreciation of ambiguity might be harder to achieve than for outside observers. Frustration could overwhelm other responses, but with psychological distance, perhaps years later looking back, even the investigators might appreciate the beauty of the intellectual challenge they wrestled with, regardless of whether they solved it. The beauty of ambiguity thus offered alternative way of valuing the 3i/Atlas investigation beyond its scientific outcomes. The process, the plurality, the mystery itself all had aesthetic worth. This appreciation didn't require abandoning desire for clear answers. One could both want resolution and find beauty in unresolved complexity. But it expanded what counted as valuable about scientific investigation, including dimensions beyond just producing definitive knowledge. Looking back on the entire investigation, we can identify several lessons that 3i/Atlas taught about astronomy, science, and the nature of knowledge, lessons that extended beyond the specific case. The first lesson was about the diversity of small bodies in the galaxy. Before interstellar objects were discovered, we knew solar system comets and asteroids came in varieties, but we might have assumed they represented universal types. 1i/Oumuamua, 2i/Borisov, and 3i/Atlas showed that objects from other stellar systems could be dramatically different from each other and from solar system objects. The second lesson was about observational limits. 3i/Atlas demonstrated how challenging it is to study faint, distant, transient objects definitively. Despite using some of the world's best telescopes and most sensitive instruments, observations were limited by resolution, signal to noise, systematic errors, and observing time. These limitations weren't failures but reflected fundamental constraints on what can be learned about such objects with current technology. Recognizing these limits was important for designing future missions and instruments. What capabilities would be needed to study interstellar visitors more definitively? What technological advances would make the biggest difference? The answers guided planning for future surveys and prompted proposals for specialized instruments or even spacecraft missions. The third lesson was about the relationship between theory and observation in astronomy. 3I/Atlas showed how models and observations constrain each other loosely when data is ambiguous. Theory couldn't definitively predict what would be observed because it had too many uncertain parameters. Observations couldn't definitively test theory because they were too noisy and incomplete. This loose coupling meant progress required iterative refinement, observations suggesting theoretical ideas, theories guiding new observations back and forth. The lesson was that scientific progress isn't always linear from observation to understanding, but can involve prolonged periods of ambiguity where multiple possibilities remain viable. The fourth lesson was sociological, about how scientific communities handle uncertainty and disagreement. The diversity of interpretations showed that science doesn't always reach quick consensus. Different researchers with different backgrounds, approaches, and biases could look at the same data and reach different conclusions. This was normal, not pathological. The community's ability to maintain productive dialogue across these differences while continuing investigation demonstrated science's self-correcting properties at work, even when correction took time. The fifth lesson was about expectations and surprise. 3I/Atlas was expected to be straightforward but turned out to be complex. This reminded us that nature often surprises. Our theoretical frameworks and categories might not capture reality's full richness. Room should be left for unexpected phenomena that don't fit existing boxes. This lesson encouraged intellectual humility and openness to revising understanding when observations demand it. The sixth lesson was about the value of systematic surveys. 3I/Atlas was discovered by Atlas, an automated survey designed to find asteroids. Without such surveys, it would likely have been missed. As survey capabilities improve, more interstellar objects will be found. This will build statistics, provide comparison samples, and allow distinguishing typical from exceptional. The lesson was that systematic observation of large sky areas repeatedly is essential for finding rare transient phenomena that targeted observations would miss. The seventh lesson was about interdisciplinary connections. Understanding 3I/ATLAS required expertise from multiple subdisciplines: orbital mechanics, thermal physics, spectroscopy, structural mechanics, chemistry. No single researcher had all necessary expertise. Progress required collaboration across specialties, with experts contributing different perspectives. This highlighted science's increasingly collaborative nature and the importance of communication across disciplinary boundaries. How to convey scientific uncertainty honestly, without undermining confidence in science generally. How to engage curiosity about unresolved questions. The experience provided lessons in science communication that would apply to future cases where public interest meets scientific ambiguity. The ninth lesson was about the provisional nature of scientific knowledge. What? We thought we knew about 3I/Atlas early in the investigation changed as more data accumulated. This revision wasn't failure but science working as intended, updating beliefs based on new evidence. The lesson was that scientific claims should be held tentatively, ready to update. The 10th lesson was perhaps most profound, that the universe still holds mysteries that sophisticated investigation doesn't quickly resolve. Despite our technological capabilities and theoretical sophistication, nature can still puzzle us. This wasn't cause for despair, but for appreciation of reality's depth and complexity. The lesson was humility before the vast cosmos and recognition that knowledge is always incomplete. These lessons, taken together, made 3i/Atlas valuable beyond any specific facts learned about the object itself. It became a case study in how science works, what limits it faces, and how it progresses despite those limits. Future students studying philosophy of science or history of astronomy might look at 3i/ATLAS as an illustrative example of science dealing with ambiguous phenomena. The lessons would outlast any eventual resolution of the specific mysteries, contributing to broader understanding of scientific investigation and human knowledge. As we approach the end of our exploration, it's worth contemplating what might eventually resolve the mysteries of 3i/Atlas and whether resolution will ever come. The object itself is gone, receding into interstellar space beyond detection by current instruments. Direct observation of 3i/Atlas specifically is no longer possible and won't be again unless some future probe overtakes it. This means resolution of its mysteries, if it comes, will be indirect. Through observations of similar objects or theoretical advances that retrospectively explain the anomalies. The most likely path to partial resolution is discovery and detailed study of additional interstellar comets. Each new example provides comparison data. If future visitors show similar anomalies to 3i/ATLAS, patterns might emerge that suggest common causes, if they're all different. That would indicate interstellar objects are diverse enough that generalizing from individual cases is problematic. The upcoming Vera Rubin Observatory, beginning operations in 2025, will dramatically increase interstellar object discovery rates. Projections suggest detecting perhaps 1 to 5 per year once fully operational. Over a decade, dozens of examples will accumulate. This sample will be large enough for statistical analysis of properties, correlations, and anomaly rates. If 10% of interstellar comets show shape evolution like 3i/Atlas, that suggests a common mechanism worth investigating. If 3i/Atlas was unique in this regard, that isolates the mystery to its specific properties. Future observations will also benefit from improved instruments. The Nancy Grace Roman Space Telescope and extremely large ground-based telescopes will provide better resolution and sensitivity than available in 2024. These capabilities won't help with 3i/Atlas itself, but will allow more definitive characterization of future similar objects, potentially resolving ambiguities that plagued earlier observations. Spacecraft missions to interstellar visitors remain aspirational, but aren't impossible. Several concepts exist for rapid response missions that could be launched within months of discovery to intercept approaching objects. Such missions face enormous technical challenges, rapid targeting, high delta V requirements, power and communication at large distances. But they aren't physics impossible, just engineering difficult and expensive. If a spacecraft ever reaches an interstellar comet, the data would far exceed anything from remote observation. Direct imaging, in situ composition measurements, structural characterization would answer many questions that remain mysterious from telescopic observation. Whether this happens in the next decade, century, or ever depends on funding priorities and technological development, but it remains possible. Theoretical advances might also contribute to resolution. Better models of cometary physics, incorporating more realistic material properties and structural complexity, might explain observations that currently seem anomalous. Research motivated by 3i/ATLAS's mysteries is developing such models. Even without new observations, improved theory might show that existing data is actually consistent with natural processes when modelled correctly. Laboratory experiments studying ice physics, sublimation dynamics, and structural mechanics under realistic conditions could provide key insights. What tensile strength does comet-like material actually have? How does it deform under realistic stress? Answers to these questions from experiments could constrain interpretations of observations and resolve some ambiguities. Archival research might also help. Were there features in the observations that were overlooked initially? Could reanalysis with new techniques extract additional information? As analysis methods improve, and as researchers with fresh perspectives examine the data, new insights might emerge from observations already in hand. The resolution of 3I/Atlas's mysteries might be gradual and incomplete rather than sudden and definitive. Different questions might be answered at different times by different approaches. The shape evolution mystery might be resolved by observing similar behavior in other objects and developing theoretical models that explain it. The spectroscopic anomalies might be clarified by better molecular databases and laboratory measurements. The trajectory puzzles might yield to improved non-gravitational force models developed and tested on multiple comets, or the mysteries might persist indefinitely. If 3I/Atlas was truly unique, if its specific combination of properties never recurs in observed objects, some questions might remain permanently open. This possibility was uncomfortable but realistic. Not all scientific questions get answered on human timescales. For the researchers who worked on 3I/ATLAS, most would likely not live to see full resolution if it comes decades hence. Their contribution was documenting the observations and posing the questions, even if answering them fell to future generations. This intergenerational nature of science, where one generation's mysteries become another's solutions, is part of scientific tradition. We build on what came before and prepare groundwork for what comes after. 3I/Atlas's legacy would be the questions it raised and the attention it drew to interstellar objects as important targets for study. This legacy didn't require resolution to be valuable. The object taught us what we needed to learn and what remained to be learned about visitors from other stellar systems. This teaching function was complete, even if the specific lessons about 3I/Atlas itself remained incomplete. As years pass and 3I/Atlas recedes further from memory, it might become a footnote in astronomy history or a memorable case study, depending on whether its mysteries are eventually solved and what solving them reveals. But for those who studied it intensively during its passage, 3I/ATLAS would remain the mysterious visitor that defied easy explanation, teaching through its resistance to understanding as much as through any facts it revealed. Thank you for journeying with me through this long exploration of deepening mystery. This story of how intensive scientific investigation sometimes reveals not answers, but richer, more fascinating questions. I hope you found peace in this exploration, discovered calm in embracing uncertainty and ambiguity, rather than demanding resolution. Sometimes there's profound comfort in accepting that not everything can be known, that mystery is part of nature's character. 3I/Atlas came from the stars, showed us puzzles we couldn't solve, and departed back into the cosmic dark carrying its secrets with it. Whether those secrets will ever be revealed, whether the questions it raised will eventually find answers, remains uncertain. Wherever you are now, I hope you're ready for deep rest. Your breathing has found its gentle rhythm. Your mind has released its need for certainty and closure. The questions we've explored perhaps help you accept the many questions in your own life that don't have simple answers. Sleep well tonight, knowing that the universe is richer and stranger than our understanding captures. Objects visit from the stars carrying mysteries we might never fully solve. The cosmos maintains its capacity to surprise us, to resist our attempts at complete explanation, to remain wonderfully, beautifully mysterious. Dream peacefully of visitors from distant suns, of observations that raise more questions than they answer, of the boundary between knowledge and mystery that shifts but never disappears. Dream of a universe complex enough to exceed our frameworks for understanding it. Good night. May your sleep be undisturbed and restorative. May tomorrow find you refreshed and renewed. And may you carry forward an appreciation for mystery as a permanent feature of existence, for questions as valuable as answers, and for the beauty and phenomena that resist simple explanation. The more we study 3I/Atlas, the less we understood it, and perhaps that is exactly what we needed to learn, that understanding is always partial, that nature exceeds our categories, that mystery is not the enemy of knowledge but its companion. Good night.